Welcome to this exploration of modern physics. Have you ever wondered why we needed a shift from the classical physics we knew for so long? Why, after centuries of relying on theories from Newton and others, did scientists feel the need to develop an entirely new set of principles? In this video, we will dive into the questions that classical physics could not answer and explore the revolutionary ideas that gave birth to modern physics. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the third lesson in understanding modern physics. In order to understand the limitations, what we do is that first we understand what were the limitations of the classical concept of time. Now, ever since Albert Einstein framed his special theory of relativity, the entire scenario of physics changed, and a framework developed by Galileo and Isaac Newton showed certain amount of limitations, showed certain amount of restrictions, which was explored by Albert Einstein. The basic idea that we get is that the laws of physics are the same in all inertial reference frames. This means that the laws of physics are the same for an observer at rest and an observer moving at a constant velocity. We also came to know that the speed of light in a vacuum is the same for all observers, regardless of their relative motion in the source of the light. In order to do this, Albert Einstein developed what is called a thought experiment, or what is called, in German, the word is called Gedanken. So a thought experiment is actually an imagined scenario, not always a real scenario, which is used to explore the implications of a theory or concept without making any physical experimentation. And it actually involves mental simulation of an experiment or situation to understand the principles of or the predictions of a theory. Now, in order to make this kind of a thought experiment, what we would do is that we will take two protons, and we know that in high energy collisions many new particles can be produced, out of which there's a particle which is called a pi meson or a pion, which is discovered. Now, in general, I'm not going into pi meson because that would be again a part of particle physics, but actually pi mesons or pions belong to the meson family, and there are three types of pions: the positive, the negative, and the neutral. So if I go by the quark composition, then the I would say the zero pion or the neutral is mixture of an anti-up down and anti-down quark pairs. Negative is basically down quark and anti-up quark, and the positive is up quark and anti-down quark. Now, pions actually have a very important role as mediators in the strong force and binding protons and neutrons together. Now, for example, if you take again a thought experiment, that when the pions are produced at rest in the laboratory, they are observed to have an average lifetime. Now, you might ask me a question: what is average lifetime? The time between the production of pion and decay into other particles. So the average lifetime is around 10.9 nanoseconds, which comes to 26 ns or something like that, which comes to 10.9 seconds. On the other hand, if you take a pion which is observed in motion, to have a different lifetime. So if it is moving at the speed almost 91.33% of the speed of light, then again it is showed that it has got an average lifetime of 63.7 nanoseconds. So from here, what we first get, that both are the same particles, but one is at rest and the other is at motion. So from here we come to know that the same particles do not have the average lifetime. One is at static, one is moving. So the concept actually starts changing from here. Now, let us imagine this to be an experiment in a kind of a laboratory situation, or a situation where we get two different kinds of observers. Here you can see that observer 1 is at rest and is standing still within the laboratory, and the observer 1 sees this pion moving at a relative velocity of, say, about 91.3%. It measures the lifetime to be 63.7, which we have seen that while it was moving, how much lifetime it gains. Now, in another situation, observer O2 is moving with a velocity of minus v to the left. This means that O2 is moving relative to the laboratory. So what happens is that from O2's perspective, this pion is at rest. This pion is at rest because O2 is moving with the same velocity as the pion, making it appear stationary from O2's frame of reference. And what it measures, that observer O2 moving relative to the velocity actually measures the lifetime to be 26.0 nanoseconds. That means it is at rest. So from here what we can get is this, that two observers measure different values for the time interval between the same events, that is the movement of the pion. So from here what we can say, that according to Newton, time is the same for all observers. Newton's laws are based on this assumption. However, the pion experiment clearly shows that time is not the same for all observers. That indicates the need for a new theory that relates time intervals measured by different observers who are in the motion with respect to each other. So this experiment clearly shows our classical concept of time doesn't work over here, and it is not the same for all observers. So this is basically the limitation in terms of the classical concept of time. We now come next to what are called the limitation of the classical concept of space. And this case also we will do a thought experiment. We will take a kind of a setup like this, and we will observe that there are two markers in the laboratory, one which makes the creation of the pion and another is the decay, or the when it destroys the pion, and both of them are being measured by a distance, for example d1, between the markers, and is the equal to the speed of the pion, which would be multiplied by the interval. So the observer over here, what he sees is this one. So what do? We take 2.737 times 10 to the power 8 m per second, which is the speed at which it moves, and we get the speed of light, and this is the average lifetime of motion. Remember, it is the time between the pion's creation and the decay, and we get in this laboratory setup, which is noted by a dotted triangle, dotted rectangle, it is 17.4. Now we take the same kind of a setup where again there are two markers, and what is happening now is that this pion is moving at this speed and the observer B is also moving. So when this pion is moving at this speed, the observer 2 is also moving. Then what happens is that this observer is moving in this speed, and what we get is that it seems to the observer that the pion is stationary. So we have two observers in relative motion. First of one, where the observer is at rest, sees it at 17.4 meter average lifetime, and the observer is also moving and the pion is also moving. And this movement is actually given by this green arrow, and the laboratory seems to move what at 2.737 10 to the power 8, that is the speed of light, and what we get is that multiplied with this 26.0, which is the pion's value when the pion seems to move, and we get the value as average lifetime at rest, we get it at 7.11 m. So we have two observers in relative motion moving different values for the same interval in the case of distance between the two markers in the laboratory. So here we get 17.4, here we get 7.11. This indicates that the physical theories of Galileo and Newton, which are based on the assumption that space is the same for all observer, and so length measurement should not depend on relative motion. This pion experiment shows that this cornerstone of classical physics is not consistent with modern experimental data. But remember, in this case, for the case of a D2, the pion should be moving at close to the speed of light, rushing at a speed of this. And the time between passing the first and the second markers showed that the creation and decay of the pion in the laboratory is 26.0 ns. So the pion experiment, again to tell you, shows that the Galileo and Newton's laws of motion, or the ideas based on space and time, really doesn't work. Now the limitations of the classical concepts also shatters when we look into the concept of what is called a velocity. Now remember that in classical physics actually there is no limit in terms of velocity, and that a particle can reach. So one of the basic equations which you know of kinematics is this, which shows that if a particle experiences an acceleration a for a long time t, velocities at large as desired can be achieved, perhaps maybe moving at the close of the speed of light. Now for this kind of an example, again a thought experiment, we take an aircraft which is moving at a speed of 200 m/s relative to an observer on the ground and launches a kind of a missile which is 250 m/s. So what happens is that on the ground, what the ground-based observer measures the missile is just the addition of these two, and he gets 450 miles per second. That is the ground-based observer which measures it. Now, this is just per as the classical velocity addition. Now, we can apply the same reasoning at a spaceship which is moving at this speed. Okay, and again there is a missile which is being fired at this speed, 2.5 on 10 to the power 8 m per second. This is 2.0 into 10 to the power ms per second. And what happens is that the observer which fires the missile and the observer at the space station observes this simply by adding this and this. So we would expect the observer at the space station to measure the speed as 4.5 into 10 to the power 8 ms for the missile. Now this speed, as you can see, I have highlighted in box, actually exceeds the speed of light. And allowing speeds greater than the speed of light leads to a number of conceptual problems, difficulties such as the reversal of the normal order, and this is something which is not allowed in Einstein's special theory of relativity. So this again shows that there is a discrepancy in terms of simply adding the velocities as per classical physics. We again take into a kind of a modern, so this is not allowed. We again take this kind of a modern experimental results. For example, we again take a thought experiment, and we say that, for example, in this kind of a laboratory setup, this pion is moving, which is moving through the laboratory at a speed of this, and this pion which is moving decays into another particle, subatomic particle, which is called a muon. And remember, this muon has to actually move when it is emitted, moves in the forward direction with a speed of this one. So according to this, if I take an observer which is observing, then again I get around 3.550 into 10 to the power 8 m per second. So this one and this one gives to this one. Again, as you see, this is more than the speed of light, because the speed of light has exceeded. This should be around should be within the range of the limit of the speed of light. So the observed velocity of the muon exceeds the speed of light. Clearly, the classical rule for the velocity addition fails and cannot work in this experiment. So the properties of time and space, remember, and the rules for combining velocities are essential for the classical physics of Newton. These concepts are derived from observation at low speeds, where only the speeds are available to Newton and its contemporaries. We shall discover further how the special theory of relativity provides the correct procedure for comparing the measurements of velocity. But for the time being, what we are now going to look is that there are certain things which are very weird, apart from the macroscopic world of speed, velocity and time, which also takes place in the microscopic world. What are those things which defies the rule of classical physics in microscopic world? We will look into that, and for that we are going to look into what is called the particle statistics, or the limitation of the classical theory in terms of particle statistics. Now, we know that thermodynamics and statistical mechanics are among the greatest triumphs of the 19th century, and describing the behavior of complex systems of many particles was shown using a small number of aggregate or average properties. For example, you can say temperature, pressure and heat capacity. We also know that the crowning achievement in this field was the development of the relationship between this and this, that is the macroscopic and the microscopic properties such as molecular kinetic energy and so on. Now remember that despite these great successes, this statistical approach to understanding the behavior of gases and solids also showed a limitation, a great amount of limitation. Although the classical theory gave the correct heat capacities of gases at high temperature, we will now see it failed miserably for many gases at low temperature. And in this section we are going to see that how the gases really cannot come up with a proper measurement. So the measurement is something, the mathematical calculation is something we are going to look into that. And in order to look into that, first we have to look into what is called the distribution of molecular energies, coming up into the next part of our video. Now, apart from addition to the average kinetic energy, it is also important for us to analyze the distribution of kinetic energies. For example, fraction of the molecules in the container has kinetic energies between, say, K1 and K2, just abrupt values. Now, for a gas in a thermal equilibrium, if a gas has to be in a thermal equilibrium at a temperature, for example, T, the distribution is given by this, famously, which is known as the Maxwell Boltzmann distribution. Now, why I am showing you this? Because you will see in the later part of the video, this Maxwell Boltzmann distribution really doesn't work out. Now, in order to tell you quickly about this particular equation, this N is the total number of molecules. This NE is basically what we call is the distribution function, and also we see that this NE or DE, it gives us actually the number of molecules in a very small range, right? It gives us the molecule in a very small range, and this is actually the number of molecules, and it gives the small range. And what is that range? E and DE, and this can be written something as this. Right. Okay. So we turn the page and we see this kind of a, so from here what we can show you is that this kind of a distribution pattern or kind of an energy distribution, where this Dn is actually a small number of molecules. This E is the number of molecules with a specific energy, and this is small interval, and I mean to say we have differentiated DE. I will explain this lower figure later. But from here what we can see, this equation tells that the number of molecules, if it is differentiated with Dn, and the energy range is between E and E plus DE, and this is equal to the distribution function Ne, which is multiplied by the energy interval, a small energy interval differentiated within D and E. Let us take a closer look into this kind of a figure. Here you can see that the graph goes high up over here. There's a mountain, there's a cusp. It goes up high over there, and this represents the number of molecules, the most probable energy. This part which I've just highlighted over here, this DE, is the small number of molecules which are present. This shaded area actually is the number of molecules with energies in that particular range. As I told you, E1 and E2 within that range. So the peak of the curve indicates the most probable energy of the molecule. So from here what we get is that the distribution, remember, as you can see, is not symmetrical. It has a longer tail towards higher energies. As temperature increases, the peak of the curve shifts to higher energies and the curves become broader, as you can see here. And the Maxwell-Boltzmann distribution, the equation we saw, is a fundamental concept in statistical mechanics. So this is how we do. Now, coming to the next part, the distribution of molecular energies is divided into the small strips, and each strip represents a small range of energies. So in order to, if we divide the horizontal axis, which is this part which is going on, into small intervals, then what we get is the total number of molecules in the gas, which we integrate with 0 to infinity. We get this kind of a value. You can later do this calculation. Just a little bit as a simple integration calculation. And here what we can find is this part. You can very well find it in the integral table. I've just calculated that from the table and given this equation. So in order to find the average energy per molecule, the total energy is divided by the total number of molecules N, and we do this calculation. Now from here what we can see is that the earlier equation, what does it tell? The earlier equation tells that the total number of molecules in the gas. Now if you want to find the average energy distribution, this also can be found out by dividing the distribution into strips. So we get this kind of an equation. Now if you go earlier, we see that the average energy is 3 upon 2 kT, where it is the Boltzmann constant and T is the temperature, and this can be very well written into this, which is the average energy of a molecule in the gas, which is KAV 3 by 2 kT. That means it is giving the value of per molecule. for the ideal gas, in which kinetic energy is the only energy we can have. And if you're wondering what is this 3/2, then this is the average kinetic energy per degree of freedom of a molecule of an ideal gas. So this is how we get the average energy. Prior to that, what we got is the total number of molecules in the gas. Now what is important to know is that we are coming to the limitation, but remember that Ne has a dimension of energy this, and it gives the number of molecules per unit energy. So to get an actual now the question is that how to obtain that actual molecules, number of molecules. Ne must be multiplied by an energy interval, and this Ne actually represents the density of molecules per unit energy, and remember that this is not a discrete number. So from here what we can get is this, that distribution functions are very helpful in giving a number of probability per some unit interval, which we have seen the intervals in the figure. We also get that to calculate a specific outcome, the distribution function must always be multiplied by an appropriate interval, and distribution functions provide a powerful tool for understanding the statistical behavior of systems with many particles. Now what we see till now, you see there are no aberrations, no problems, no kind of I would say violation in terms of classical physics. Everything is duly sorted. We get the Maxwell Boltzmann distribution, we get the total number of gas in molecules, then we calculate the average energy, then we get the energy which is given molecules per unit interval. Everything goes so. Now we come what we call is the polyatomic molecules and the equipartition of energy theorem, and this is where you will see that the equipartition of energy theorem actually doesn't work here in the classical system. Now in order to go a little bit more into this, first we will know that for monoatomic gases there is no problem. So translation of kinetic energy is half mv squared. And what we can see from here is that we take this energy, I mean to say the distribution energy, and we can see, you can write like this. So the first, the second and the third. And this happens when we are taking this kind of a cube. So if we are taking a three-dimensional cube and we are trying to find out the average energy, etc., then what we get x, then y and z. These are three axes. So there are three quadratic terms. That means there are 3 degrees of freedom. As simple as that. And now we calculate the average energy, which is this one. So again, remember this 1/2 of each 1, 2, 3 actually contributes to the energy part. So 3 degrees of freedom for a 3-dimensional, we get 3 quadratic terms, 3 degrees of freedom, and the average energy is this. And then we come to what is known as the equipartition of energy theorem. This is very important, and in the next part of the video I would like to explain in very simple words what is this equipartition of energy theorem. So this is how the definition goes. So in a system at thermal equilibrium, energy is distributed among all accessible degrees of freedom. Each degree of freedom, what are those? We will come to that. Translational, rotational, vibrational, contributes in an average energy of half kT per particle, where K is basically the Boltzmann constant. Now also what is important is that for ideal monoatomic gases, that means each molecule has 3 degrees of freedom, this works out. But the limitation, it doesn't apply to system with quantized energy levels. So this is the system where the thermal equilibrium energy is distributed equally, and each degree of freedom, which I was talking, translational, rotational, vibration, contributes an energy of half kT particles. For a monoatomic gas, each molecule has 3 translational degrees, so the average kinetic energy is 3/2 kT per particle. So this is the equipartition of energy theorem, and overall it tells, as I told you, that thermal equilibrium energy is distributed equally among all accessible degrees of freedom. Now the situation turns a little bit weird for what are called diatomic gas or diatomic molecules. For example, atoms which has got 2 atoms per molecule. So as you see in this kind of a figure, there are still 3 degrees of freedom associated with all translational modules, motion of the molecule. So in this figure, we can see a diatomic molecule with the origin at the center of the mass, and rotations can occur where? This where? X prime and Y prime, and a vibration, remember, can only occur along Z axis. Now, if I go back to this part of the video where I was talking about 3 degrees of freedom, so now you can understand X prime, Y prime, and the Z prime, and the vibration actually occurs in the Z prime part. So this is the actually the figure that shows you. So, and we know that here the rotational energy is given up by 1/2 I omega squared. It's a general form for the rotational kinetic energy, and we can write the energy of the molecule as this one. Now note, here we have 1, 2, 3, 4, 5. So we have 5 quadratic terms. So we have 5 quadratic terms, and what does it mean? It has 5 degrees of freedom. And according to the equipartition theorem, the average kinetic energy we know per molecule will be 1/2 kT. So it would be about around 5/2 nRT, which actually includes the, this one, E initial, or the total internal energy, I would say EINT is 5/2 nRT, and this is translational plus rotational. So EINT is the energy, which is the total internal energy, and just by taking the equipartition theorem of 1/2, we get 5/2. Why? Because we have got 5 quadratic terms. Why we have got 5 quadratic terms? Because the mathematics show like this, and the energy of the molecules come upon with 3 dimensions minus the diatomic molecules rotational energy, which is I x upon omega square and I y upon omega square. This is a rotation energy. Now what we will do is that we examine where the classical molecular distribution theory, which is a very good accounting of molecular theory, actually fails, or I would say a limitation. Now imagine we have a container of gas with a fixed volume, and we transfer this heat or energy to the gas by placing the container in contact with a higher temperature. Now all of this gas, remember, all of this are transferred energy increases the internal energy of the gas by an amount of this EINT, as I told, internal energy, and there is an accompanying increase obviously in the temperature, which is delta T. So delta E int is the increase in the internal energy, and delta T is the change in the temperature. And by the formula, we define the molar heat capacity with this. And from here, what we can get it is that 3/2 nRT, we get this one, which is monoatomic and non-rotating, non-vibrating diatomic ideal gas. We get 5/2 nRT, which can be written as CV 5/2 R for rotating diatomic ideal gas. Then we get 7/2, which is rotating and vibrating diatomic ideal gas. And CV is basically a measure of how much temperature a gas increases. Now from here, if I go to the next part, we have already seen what is the equipartition of energy. Now if we add energy to a gas, the equilibrium theorem actually tells us this energy is distributed equally among all the possible ways of the molecules, which can store up to the degrees of freedom. But for diatomic gas, and we know that for diatomic gases, the classical equipartition theorem predicts that the molar capacity would be 7/2 R, and for considering rotational translation, etc. And for monoatomic gases, the equipartition theorem predicts that the monoatomic gases should be 3/2 R for monoatomic gases, where R is the gas constant. Now typically what starts to happen is that these type of gases, for helium, neon and argon, this actually matches with the closely matches with the predicted value. So whatever with the predicted value, helium, neon, argon, etc. works perfectly well. But the problem starts with hydrogen, nitrogen and fluorine. And what we see is that the heat capacity of diatomic gases, which has got 2, is lower than the predicted value, especially at low temperatures. Now here we come, as I told you that at some part the equipartition theorem cannot predict what it is, so that is what it happens. Let us see some examples, it will be clear for us to understand. Now for hydrogen, nitrogen, or fluorine at high temperatures, if you take a high temperature, many of the diatomic gases do indeed approach the expected value of 7/2 upon R. But if I take a lower temperature, the temperature is dipping, the values are much smaller. For example, we will see values are much smaller. For example, we will see that in case of a fluorine, the fluorine seems to behave as if it has got 5 degrees of freedom. That means the value at 7 degrees of freedom at 100 Kelvin. Hydrogen again starts to behave a little bit weird. It behaves as if it has got 5 degrees of freedom at room temperature. But it has a high enough temperature at 3000 kelvins, and also the heat capacity of H2 approaches 7 degrees of freedom while at lower temperatures. So this actually is a kind of a problem, and also the classical calculation demands that CV should be constant independent of the type of the gas of the gas or the temperature. So as you can see that hydrogen at lower temperature values a little bit weird. Fluorine has got 7 degrees of freedom, and this actually does not work well with what we call classical physics. So from here what we can deduce is that the equipartition theorem, which is very successful in predicting, as we have seen, many thermodynamic properties, actually fails miserably accounting for the heat capacities. Now the question is that this theorem requires that the energy added to a gas must be what? On an average divided equally. That is why it is called equipartition theorem. But what happens is that, and classical physics also does not permit a threshold energy for any particular type of motion. Now when I say that it does not allow threshold energy for a particular motion, that means it tells that energy should go up and up and up and goes up to infinity. Now we in mathematics and physics, how can infinity be helpful? It is something we physicists and mathematicians try to avoid. So the question is that this one, that how is it possible for 2 degrees of freedom corresponding to the rotational or vibration motion which we have seen to be turned on as the temperature increased? And this is not possible. This is not possible. So in classical physics, energy is treated as continuous quantity. This means that a particle can have any amount of energy and there are no restrictions that the value can take. So from here what we get the answer in quantum mechanics. Because in quantum mechanics what we get, energy is quantized. So what I told you on the left hand side corner of the screen, threshold energy, that means quantization. This means that energy can only take certain discrete values. For a particular type of motion like rotation or vibration, there is a minimum energy level that a molecule must possess to exhibit that motion. This minimum energy level is known as the threshold energy. So here we get that we will see eventually in our course of modern physics that we really need to replace the classical Maxwell Boltzmann energy distribution with a function that is consistent with quantum mechanics, because the equipartition theorem really doesn't work with low temperatures and the gases behave weird, showing several degrees of freedom. But remember, in classical or thermodynamical way, Newtonian mechanics, this works perfectly well. So here I would like to take a pause, and this actually brings us to the next part of our series in our learning of modern physics, where we have taken review of the few of the concepts of classical mechanics. We have understood the limitation also, where it fails, the velocity, the time, the space, and in particle statistics. And we will go up into the next part of the video in the next lesson. So I would immensely like to thank you for watching this video. If you have liked, please do subscribe to my channel Physics for Students and click on the bell icon to get all the notification, and you can write to my email ID, and you can also subscribe to my other channel where I have seriously now started putting up new videos on general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will continue its journey, surprising you with more such beautiful, fun-loving and informative videos on physics and mathematics, and see you in the next video. May the good Lord be with you.